good student, but she may have a little learning curve in the process of doing things. So if there are problems or anything, let me know, and I will obviously talk to her about that. What I want to do today is go through and sort of bring together some of the things that we talked about yesterday with respect to pH and charge and buffers, and hopefully start bringing them all together first in the form of the issues of these molecules with respect to amino acids, and then with respect to proteins. Okay, so that's kind of the theme for the day. We're going to be talking, as you can see on the lecture, protein structure 1 and protein structure 2. And there are actually 3 protein structure lectures that I give, and there's a lot of stuff that we could talk about. In fact, there are entire courses that are taught about protein structure. So for right now, what I want to do is go and get us started on protein structure. Okay, so yesterday I talked about the structures of the different amino acids. And I said that you were responsible for the names of the amino acids, you're responsible for knowing which categories they fit into, and you're responsible for knowing what the ionization of each of those is. So if they have an R group carboxyl, if they have an R group amine, if they have an R group sulfhydryl, that was also one that ionized. Those are 3 different things that will ionize, and they will have, depending upon the group, either a 0 or a -1, or a 0 or a +1. And though I don't expect you to memorize the PKA values or that, I will give you that sort of information for an exam. You should know how to use those PKA values with respect to pH to predict the charges, not only of the R groups, but also the carboxyl and the alpha carboxyl and the alpha amine groups. So those will all be important. One of the simplifying things that you will discover is when we put these together into a protein, we don't have to do the charge of every single group. It actually there is one big simplifying factor that happens, and we'll talk about that as we get going along. Okay, well, if you look where I finished up yesterday, talking about the PKA values, this is a table that your book has. It's pretty nice, and students can understand a bit about what happens with ionization of these. We see first at the top we've got alpha carboxyl groups. We've got examples of these. I'm sorry, this is alpha carboxyl, which of course is found on every amino acid. We've got R group carboxyls, and they show you the examples there, and you can see the PKA values. Now, this table is a little odd in that they're not even totally consistent with their own setup. So other places in the chapter, they give you different values for the PKAs for the same thing. So we can sort of think of these as sort of approximate numbers. And the exact values isn't really essential for our purposes in understanding what's there. We look at histidine. Histidine, I pointed out yesterday, was that an interesting amino acid that was an amine that had a PKA value down around 6. And that meant that it was ionizing at a pH that was not that different from physiological pH. Okay, the pH of our bloodstream is about 7.4. 6 is not that far away, so it's a relevant amino acid for ionization at a pH of our bloodstream. The other one that's relevant in that respect is cysteine, which, depending upon which table you look at, here they have it as 8.3. Other tables you see it listed as low as 8.0. So these sorts of R groups are very, very important, as we will see, affecting the charge of a protein. The terminal amine, for some reason, they have it listed here as an 8. And it's the only place I've ever seen it in the world listed as 8. It's usually at least about 9, so don't sweat that. And again, I'm just showing you this, talking through it. You're not going to memorize these PKA values in any way. If you want an idea about what I do with PKA values, I have a practice exam that I will make available to you that you can take a look at and see, and you'll see kind of how I do PKA values on there. I'll say, well, assume that all alpha carboxyls have a PKA of 2.2, and assume all alpha amines have a PKA of 9.5, and assume all R group carboxyls have an amine of 4.4. That means you'll need to know, well, which amino acids have R group carboxyls, which amino acids have R group amines, etc., so that you can use information like that. Okay, so that is where we are there. The abbreviations I list, but the abbreviations you're not responsible for. I show them here to you only because you'll see them. Most commonly when people list protein structures, they will use the abbreviations. They won't use the full names. I'm using the full names to give you 40 less things, or 40 fewer things to memorize. So that's good. I can't even tell you the one-letter code for most of them, so it's not like something that's commonly used. Okay. Let's go to talking about amino acid ionization. Okay, so amino acid ionization is important because, as we noted, they change charge as they gain or lose protons. So if we look at this simple amino acid, you saw this, something like this the other day or yesterday, which we started with an amino acid that was a simple amino acid. It had an alpha amine. It had an alpha carboxyl right here. Our group didn't have any designation in terms of having anything ionized, so we just left it as an R. Most amino acids are in that category. We start adding sodium hydroxide to the solution. The carboxyl, which has the lowest pKa, of course, will be the one that ionizes first. And we see it losing its proton, becoming a COO-. In the process, converting this amino acid, which had a charge here on the left of +1, to having a charge of 0. So we've lost one proton. It's not surprising we go from +1, take 1 away, we're going to end up with 0. We go next to take off that proton off of the alpha amine group. We take off the other proton. Now the amino group has a charge of 0. The carboxyl group has a charge of -1, and we've gone to a charge of -1. So amino acids ionize. Anything that can gain and lose protons is going to change its charge. No question about that. So there's no surprise in anything I'm showing you there. Now, some of these that when we look at their plot for their titration curves, well, that was good. When we look at the plot for their titration curves, not surprisingly, their titration curves are a little bit more complicated than what we saw for the acetic acid. Acetic acid only had one proton that could come on or go off, and it only had one flattening because it only had one pKa value. When we have amino acids that have multiple pKa values, not surprisingly, we will see a flattening that occurs in the titration curve every place where we have a pKa value. So if we look at this, okay, so here's a bunch of amino acids. Come on. Oh, come on, yo. This thing doesn't have a good scroll. Okay, here's a good example. So here's a simple amino acid. Here's alanine. Alanine does not have an R group that ionizes, so it only has two groups that can gain and lose protons, an alpha carboxyl and alpha amine. And we see on this plot an example of what its titration would look like. The pH rises until we get into a buffering region for the first pKa, which corresponds to the alpha carboxyl group, and that's where we get a flattening in the curve. Then, once we've exceeded the capacity of that buffer, we discover that the pH rises until we get near the second pKa, where we experience buffering again. We see a flattening of the curve, and we go up here. I think you should be able to look at this graph and figure out the charge of the molecule at appropriate places. We can't really tell the pH at all places. All right? So I say appropriate places. Well, where are the appropriate places? The appropriate places are places where we're more than one pH unit away from all the pKa values. So if we look down here, for example, at pH 0, that's more than one pKa unit away from all of the pH of the pKa values. And at that point, we could predict the charge of that molecule using that rule I gave you yesterday about the proton. If the pH is more than one unit below, protons are on. So in this case, the protons are on both the carboxyl group and on the amine group. Carboxyl group with the proton on it has a charge of 0. Amine group with the proton on it has a charge of +1. So we could say right here at this point on the graph here at the bottom that the pH of this solution is basically +1. And I just realized I don't have this little microphone on. Too many things to remember. Well, the other way. Okay, so that's what happens then with respect to too much electronics. The charge there. Where else? If the tendency you're going to want to do is you're going to want to say, well, what's the charge right there at the pKa value? And the answer is I can't tell you. Why? Well, half of the molecules have the carboxyl with the proton on, which means they have a charge of +1, but half the molecules have the carboxyl with the proton off, which means they have a charge of 0. So I can't say what the charge of all the molecules are. I can only say what half of them are one, half of them are the other. But up here, when I get more than one pH unit away from all the pKa values, I say, yes, I can decide that charge. That little box there shows you the range in which I can predict the charge of that molecule. Up here, we're more than one pH unit above the pKa for the carboxyl, meaning the proton is off. We're more than one unit below the pKa of the amine, meaning the proton of the amine is on. So we have a charge of -1, +1, or an overall charge of 0. Okay? And then last, we get up here. This is exaggerating a little bit. The box should be more like up in here. But up here, we can tell the charge again because we're more than one pH unit away from the pKa value. All the protons are now off. Carboxyl has a charge of -1. Amine has a charge of 0. And the overall charge of the molecule is -1. So you should be able to look at a graph like this and predict the charges at appropriate places. And I think it's not unreasonable to think that you might be able to draw a graph like this. If I said, here's an amino acid, and here's some pKa values for it, draw what its titration curve would look like, and show me your charges as appropriate. So I think those are certainly fair game. If we look at some of the more complicated amino acids, we discover that they have a more complicated titration curve. Come on here. Okay, here's aspartic acid. And they've kind of exaggerated this because it's a little hard to tell, but there's actually up, flattening, up, flattening, up, flattening. So there's actually 3 places where this guy flattens. These 2 down below are close enough together that they sort of merge into one, which is kind of unusual. I kind of exaggerate it when I draw it. I draw three places where we get distinct flattening that happens. And we could do the same thing with this that we did with the other. Aspartic acid, of course, has an R group that is a carboxyl group, and so we have to take into consideration its pKa and its ionization. Now, Anna is going to talk about that with you probably next week, so I'm going to let her go through and do some of those for you. But you should be able to predict the charges of these molecules at any of the pH values, given the amines and carboxyls and the pKas that they have. Okay, questions on that? The pop quiz didn't teach you guys anything yesterday? Okay, all right. So let's turn our attention now to start thinking about how these amino acids come together in making proteins. So in making proteins, of course, a protein is a polymer of amino acids. There are 20 amino acids that make up proteins, and the order in which these amino acids are linked to each other give us everything, underline this, everything in terms of characteristic that a protein has. So we describe this order of amino acids as the sequence of amino acids. The sequence of amino acids determines everything, ultimately, about the protein. So the sequence of amino acids is the first order of protein structure. It's what we call primary structure. So when I say primary structure, you should automatically associate that with the sequence of amino acids in your head. So I'm going to spend a little bit of time talking about primary structure and the considerations of primary structure, the first of which is the way in which we link the individual amino acids to each other. Okay, so what you see on the screen is the chemical reaction that's involved in putting 2 amino acids together. Okay? The chemical reactions that's involved in putting 2 amino acids together. Here's one amino acid on the left. Here's a second amino acid on the right. And during the synthesis of a protein, these 2 guys are joined such that the carboxyl reacts with the amine, splitting out water. We see water coming out over here. And in the absence of that water, we create what's called a peptide bond. A peptide bond occurs between the alpha carboxyl of one amino acid and the alpha amine of the next amino acid. Okay? This process occurs, we'll talk next term about it, in ribosomes. So ribosomes are the structures in the cell that use the genetic code to put together amino acids in the proper order. Okay? So this reaction that you see right here is actually catalyzed inside the ribosome. Now the peptide bond is the sort of, I like to think of it as the sort of building block bond that's necessary for making proteins. Every pair of amino acids, or every amino acid, is linked to its succeeding amino acids and by the amino acid in front of it by a peptide bond. Now, if we look at what we have just made here, we started with 2 amino acids, and we ended up with something where the 2 amino acids were joined together. And these 2 amino acids being joined together created something where we didn't have 2 amino acids anymore. We now created what we would call a dipeptide. A dipeptide would be a molecule that would have 2 amino acids that are joined together by a peptide bond. Okay? 2 amino acids joined together by a peptide bond. That's what we see is going on right here. If I add another amino acid to it, I will create a tripeptide, obviously. I add another amino acid to it, I'm going to make a tetrapeptide, et cetera, et cetera. Okay? Does that screw that up if I do that? No? It's odd. Okay. Okay. So a polypeptide is a polymer. That is, we have many amino acids joined together by peptide bonds. I use the term polypeptide and protein interchangeably. There is a technical difference between the two, but I won't go through that technical difference here. Okay? It's not important for our purposes. So the term polypeptide and the term protein I will use interchangeably in this class. Okay? Now, so we join these guys together. Another thing I want you to notice in looking at this is that a protein, and yes, this is a protein. It's a specific protein. It's a dipeptide. But a protein has 2 distinct ends. One end of a protein will always have a free alpha amino group. Here is the free alpha amino group. Oop, where did I lose my thing? Right here is the free alpha amino group. All proteins will also have a free alpha carboxyl group over here. All right? So we can think of these 2 things as ends of a protein. One end is an amino end, because it's the only place in the protein where we have a free alpha amino group. We don't get a free alpha amino group anywhere else because, hey, we had an alpha amino group here and we had an alpha amino group here, but this guy got gobbled up in the peptide bond. This is no longer a free alpha amino group. It's now in the context of a peptide bond. So all proteins will always have a single free alpha amino, and it will always have a free single alpha carboxyl. Now, the beauty of that, for the purpose of calculating charge, is that this amino in here in the peptide bond and this carboxyl in the peptide bond, neither one of them can ionize. Things just got simpler. Okay? So these guys cannot ionize. We start thinking, well, what can ionize in a protein then? Okay, I'm going to show you. What can ionize in a protein? Obviously, the alpha amino can still ionize. The alpha carboxyl can still ionize, but we only have one each of those. What else can ionize in a protein? The R group. So anything that has an ionizable R group can also ionize. So if we want to determine the charge of a protein, all we have to do is figure out the charges on the alpha amino, the alpha carboxyl, and any relevant R groups. Not all R groups will ionize. Okay? So when I go to calculate a charge of a protein, that's the first thing I do, is I sit down and I mark on the protein where the individual things that can ionize are found. Then all I've got to do is use my rule to apply pH and pKa to each one and decide what the charge on each one is, and then add the overall total up. Does that make sense? At least one nod. Everybody else is just nodding off. I'm sorry. Can you give an example? Can I give an example? I'll tell you what, I have an example on one of the videos online, so that might be the best way to do it. But an example would be just sort of the order like I told you here. Would be to go through and decide for each one. Let me see if I have something on the notes here. If I do, I can do something here for you, Anicia. What did I do? Oh, wrong thing. Oh, did it again. Come on. Let's not do that. All right. Let me think. Peptide bond. Okay, I think I do have one here, actually. Yeah, here's an example. Okay. It's not a good example, but we can do it. All right. Why is it not a good example? Well, you'll see why. Let's say I told you here is a polypeptide chain, and I would like you to calculate the charge on it. So as I told you, the first thing I would do is I would look through this polypeptide chain, and I would say, well, which of these groups are going to ionize? First of all, I know there's got to be an alpha amino, and there's my alpha amino down here on the end. So that can have a charge. This guy over here, the alpha carboxyl, can have a charge, right? And now I say, well, how about the R groups? Can this guy have a charge? Well, technically this can, although it's very unusual. The answer basically for us is no. This guy's a glycine. Glycine can't have charges, no. Glycine can't have charges, again, no. Phenylalanine can't have charges, no. Leucine can't have charges on the R group, no. So the only two things that are going to affect the charge here are going to be the alpha amino and the alpha carboxyl. So if I said to you the pH of the solution is 6, and the pKa values for alpha amines is 2.2, and alpha carboxyls is 2.2, and alpha amines is 9, we would say, well, 6 is more than one pH unit above the alpha carboxyl, so the proton would be off. And the pH is more than 1 unit below the alpha amine, so the proton would be on. And this guy would therefore have a charge at pH 6 of 0. Yes?
Why doesn't hydroxyl and tyrosine associate?
So, as I said, at very high pHs, it turns out tyrosine actually can, but to keep things simple, I describe it as if it doesn't. Yeah, but it can. It can. Okay, now, I might ask you a question. I might say, okay, here's the same pH I gave you. pKa of 9 for the alpha amino. pKa for 9 of the alpha carboxyl. Of 2.2 for the alpha carboxyl. I can't even talk. What's the minimum pH at which this guy would have a charge of -1? What's the minimum pH we have a charge of -1? Anybody know how to do it? What's that? So pKa of alpha amine of 9 and alpha carboxyl of 2.2. Nobody knows? Would have been a good pop question, pop quiz question. All right. This polypeptide, same one I just showed you. Alpha amine has a pKa of 9. Alpha carboxyl has a pKa of 2.2. I'm asking you, what's the minimum pH at which this guy would have a charge of -1? I hear an 8. I hear a 7. I hear a 10. Okay? The answer is 10. Why 10? Well, 10 is the lowest pH at which both protons would be off. That's what it takes for it to have a charge of -1. Right? Because the pKa is 9. We have to get at least one pH unit above the last pKa to get that there. Okay, so that's the kind of things that you can do with pKa values and so forth. So that's good. This figure here is actually it's a good and it's a bad figure. And the reason it's a bad figure is they have 2 glycines, and I don't know why they chose to pick 2 glycines. It wasn't as if they didn't have enough amino acids they could pick. Maybe their artistic budget was low that month, and so they decided they could only afford to repeat the same amino acid. But this figure I like in the sense that it shows you something about a nice schematic of a protein. Okay? Look at what's happening here. Look at the orientation of the R groups. The R groups on the first one are pointed up. The R group on the second one is pointed down. Third up, fourth down, fifth up. The R groups are orienting themselves as far away from each other as they can. That's not surprising. Atoms don't like to be put into too close a proximity. There's an enormous energy to be overcome if you try to squeeze 2 atoms together. That enormous energy gives rise to a phenomenon we know as steric hindrance. And steric hindrance basically means that you're not going to put 2 atoms too close together. There's a certain boundary region that you are not going to squeeze things together. So molecules that are full of atoms arrange themselves so they don't have considerations of steric hindrance. We'll see that's important when we get to thinking about protein structure. So this gives us a nice example of that, and it's a nice schematic example. We have, notice again, we have the free amine at one end, we have the free carboxyl at the other end. Now, proteins are made in the direction from amine to carboxyl. We start with the amine end, and we build in the direction of the carboxyl end. Okay. Why does that keep doing that on me? Doesn't like me. Okay. All right. Let's see. Schematically, this shows us what you saw in the last figure. R1 up, R2 down, R3 up, R4 down. So these guys are arranging themselves so as to avoid as much as they can each other. Even there's a problem. Okay? And I should point out something else, that this arrangement that we think of is in what we call the trans orientation. Even though there's not a double bond here, they're arranged on opposite sides, kind of like hydrogens are across a trans double bond between two carbons. So this trans orientation is strongly preferred. It's not absolute, but it's strongly preferred. And that brings up another subject that is very important for understanding the overall structure of proteins, and that's peptide bond resonance. Okay? Peptide bonds can exhibit what are called resonance structures, and they're just alternate electronic configurations, are really all they are. But those alternate electronic configurations give rise, as you see on the right, to a double bond. Now, I hope you remember from your organic chemistry that double bonds can't do something that single bonds can do. What is it that double bonds can't do? Can't rotate. So when we have a double bond, it leads to inflexibility. It leads to locking things into configuration. And it turns out that the peptide bond behaves like a double bond more than it behaves like a single bond. Behaves more like a double bond than it behaves like a single bond. Now, that turns out to give us yet another simplification for understanding protein structure, as I will show you in just a minute. It's important to recognize that peptide bonds behave as if they were a double bond, not a single bond. So for our purposes, we're going to treat them like they're double bonds. All right? Now, I want to remind you we have three relevant bonds here. We have a bond between the alpha carbon and the alpha carboxyl. We have a bond between the alpha carboxyl and the alpha amine. And we have a bond between the alpha amine and the next alpha carboxyl. Three relevant bonds for every single amino acid that's in that polypeptide chain. One of those three bonds behaves like it was a double bond. This guy right here, the one in the middle, the peptide bond. Okay? The other two, they act completely like they're single bonds, and they can completely rotate. They have complete freedom of rotation. So when I said a protein was flexible, I was not exaggerating. Part of it is inflexible, but two parts of it are very flexible. Okay? Now, what that does, in effect, is it basically locks a configuration right here. Okay? It locks this configuration. I would like you to think for the moment that my nose is this double bond. Okay? One nostril is the carbon, and one nostril is the nitrogen. Are you with me? Okay? If I take those nostrils and I look at the other things that are around it, okay, right, then I see that they can rotate relative to my nostrils. Okay? They can rotate relative to my nostrils. My nostrils are locked, but the bonds around there are completely able to rotate. All right? Rotating here versus rotating here. I'm probably going to screw that thing up. All right? Everybody understand that rotation? For every amino acid in that polypeptide, I have two angles that can rotate. They're called phi and psi. And for our purposes, it doesn't even matter which one is phi and which one is psi. Okay, that's one less thing for you to memorize. But the very important thing is that I can, in fact, predict what angles of phi and psi can exist. What angles of phi and psi can exist? Now, that's a very important consideration. You might say, well, why not all angles? You said it could rotate. And it turns out when we look at the possible rotational angles, we discover that not all angles, in other words, it can't rotate a full 360 degrees. Why do you suppose that might be the case? Steric hindrance. And what's going to play a role with steric hindrance? R groups. R groups, R groups, R groups. Okay? The bigger the R group, the more likely we're going to have steric hindrance. Okay? So, there's a person who first made this observation many years ago. He's an Indian scientist named Ramachandran. He's a very famous biophysicist. And he, that keeps going down there. I put it up there. Oh, I know what it is because it's not aligning on here. That's the difference. So, on here it's aligning on that thing. On here, it's, oh, I've got to look up on the screen instead of doing that. Okay. All right. Well, I have to, one of the technical issues. All right. Ramachandran, oh, now you. Ramachandran recognized this limitation. And he said, you know, if we understand, if we think of the peptide bond as a double bonded structure, then that's a great simplification for us. So instead of having three possible angles of rotation and all kinds of possible problems, in fact, the two possible rotations that we can have really make it simpler. Come on, you. What are you doing there? All right, try it again. Okay. So Ramachandran did this. Now I'm going to show you the plot. I'm going to show you some other things after that in a second. Ramachandran said, I can tell a computer all the information about size, about steric hindrance, about energy, and I can ask that computer to take and rotate in space this imaginary molecule around an alpha, around a psi bond or a phi, which single bond that we want to do, and using those angles, predict the stability of the structure that arises solely as a function of steric hindrance. Solely as a function of steric hindrance. All right? When he did that, the computer then spit out a plot that looks like this, where these are probabilities of stability. And what he discovered was something that was pretty cool. He discovered that there were two primary areas of stability that exist for these particular angles, okay? So, and you don't need to memorize these or anything, but here's a phi bond. I'm sorry, this is a psi bond. A psi bond with an angle of about 120 paired with a phi bond of about 120 gave a nice, stable structure, okay? A psi with a of minus 60 with a phi of minus 120 gave a nice stable structure as well. But things out here with a minus 120 with a 120, those weren't stable. The greenest areas are the stablest. So from a theoretical basis, Ramachandran was able to say that there's two very common angles that we can expect to have in amino acids and proteins based on simply theoretical background. Everybody with me? So that's what a Ramachandran plot is. It's a plot, it's a theoretical plot of stability. And there's two primary areas of rotational angles that give that stability. Now I'm going to show you in a second how those line up with the real world proteins that we actually know of. Okay? But his theoretical plot told us that there were going to be two primary ones of consideration. Well, this is pretty cool because when we look in the real world, we discover that there are two primary common structures that we find in proteins. Okay? I say primary. Primary is not the best word because primary refers to primary structure, and the structures themselves are called secondary structures. But these two structures are called an alpha helix and a beta strand. Your book calls it beta sheets, but it's actually a beta strand. Okay? Linus Pauling was able to demonstrate the very similar thing. Linus Pauling won a Nobel Prize for this. Okay? Now, I'm going to come back to those two structures in a bit, but I want to take a slight diversion and show you again just a little bit more of some things that we see in polypeptides. Okay? So if we look at, there's our overall polypeptide. If I said to you which bond here is the one that is the bond that is mostly planar, which one would you say? Okay? So it's going to be the CN. It's going to be this peptide bond right here. The phi and psi's are going to be this one and this one. Okay? And that would be the case. Okay? If we look at cis and trans, okay, we can see within a given amino acid how we can arrange the, within a given dipeptide, how we can arrange those groups. Here are the two groups that are, here's an R group here in green, here's an R group in here. They're oriented in the trans configuration. As I said, it's not absolute. They can be oriented in the cis, but when we start putting them in the cis, we say, whoops. We start to see that they're going to start running into each other, and what Ramachandran said was right. Okay? That there's going to be angles that really aren't going to be very favorable, and those angles might very well be dependent upon which R groups that we're talking about. The R groups are going to influence which structures are stable. Okay? All right, so this was a very important observation made by Ramachandran. Now, I want to show you one of the odd amino acids. Proline. Anybody remember why proline was of interest to us? Proline was the one whose R group came back and made a bond with the alpha amino group. It was the only one that had a ring structure involving the alpha amino group. And the thing I said about proline was that proline was not very flexible, right? Frequently, because of its inflexibility, proline will cause some limitations on structures that can exist. Proline is odd in another sense. Proline is, of all the 20 amino acids, the one that is the most likely to adopt a cis configuration when it's in a polypeptide. It's the most likely one to be found in a cis. So we start seeing that again, there's some odd things about structure that are going to govern the next level of protein structure. We're going to come to that in just a second. But I want you to keep in your mind that proline is very odd in that sense. And proline is something that we will see is very much associated with what we call bends in a protein. Okay. Let's see. I don't think this is of anything. Yeah. There's your phi and psi. Okay. The rotational angles that you can see. Okay, and now we're ready to talk about the next level of protein structure. Okay, so any questions about primary structure? Yeah.
I have trouble seeing why the proline is, the trans looks like a cis to me.
Yeah, proline, it's a little confusing because proline is, so here technically is the R group, and you're saying that this looks like this guy is bonding over here. It does look like that. What can I tell you? The problem is what they've done is so there's two rotations, okay? In the trans, this guy is farthest away from this piece, whereas in this guy, it is closest to the same piece. You're not going to have to draw the structure if that's your concern, okay? So I couldn't draw this structure. So, but the point is that with the ring, you've got two different ways to orient that ring. And so they've got a convention for one side of the ring versus the other side of the ring is all it is. Okay. Okay. Now, when I say the proline can exist in the cis configuration more than any other amino acid, it's still only about 1 in 100. Okay? About 1% of the time. For the other amino acids, it's like 1 in 10,000. It's not very common at all that it's in the cis configuration. So proline is an oddball, but it still very much prefers to be in the trans configuration. Okay. Let's see. It won't let me do that, will it? Okay, let me move that over. That's better. Okay. Now, if we look at the next level of protein structure, it's what we call secondary structure. And I've already started talking about it because secondary structure is different from primary structure. It is another structural layer. So with proteins, there are 4 layers of structure to consider. Primary structure being the sequence of amino acids. With secondary structure, we start thinking about the shape of the protein. Because the protein is a polymer, and it has some shapes within it. It has shapes within it. All right? So we could think of, for example, my hair is not a good example, but your hair might be better than mine. We could think of your hair having individual hairs would be something like primary structure. We could think of the curl of one of those hairs being a secondary structure, and we could think about how all those hairs come together in your head to make tertiary structure. Okay? So we have an overall shape, we have individual shapes. Okay? The difference in a protein being that instead of having individual hairs, all the hairs are connected as one big one. Everybody with me? Okay. So we're starting to talk about the curliness of hair. The curliness of protein structure is what we're talking about. All right. So let's think about that right here. We see the first of those structures. This was that first theoretical structure. This is, in fact, what we call an alpha helix. An alpha helix, and maybe I should define secondary structure before I even talk about an alpha helix. So a secondary structure, the definition of a secondary structure is a structure in proteins that is a repeating structure. In other words, it's repeating. We see it over and over. And it arises from interactions that are between amino acids close in primary sequence. And I'll repeat that in a second. It's arising between amino acids that are close in primary sequence. So, a secondary structure of a protein is a structure of a protein that is repeating, and it arises from interactions between amino acids close in primary sequence. Now, I'll show you what that means in real terms. Okay? It's a structure in a protein. It's a repeating structure. So in this case, the repeat is a helix. We see it going on and on and on. It doesn't go on forever, but it goes on for a ways. So the repeating structure here is this coil known as an alpha helix. It arises because of interactions between amino acids that are not very far apart in primary sequence. Okay? Well, what does that mean? If I look, for example, I'm going to do it again, aren't I? There, that is off. Okay. It arises, okay, here is a schematic of very similar polypeptide sequence that you saw before. And what this is showing you are the interactions that are happening between one carbonyl group of one amino acid and a hydrogen of another. When this guy coils, they're brought into close proximity. That's actually what we saw. Let's go back to our figure. That's actually what we saw in this very first figure. Here, for example, could be amino acid number 4, and here could be amino acid number 10. They're close in primary sequence because they're only 6 amino acids away from each other, but the coiling has brought these two close enough that a hydrogen bond is forming between them. Hydrogen bond is giving stability to this structure. Just like covalent bonds give stability to the polypeptide, hydrogen bonds are giving stability to the alpha helix. The primary forces that help to stabilize an alpha helix are hydrogen bonds. Now, hydrogen bonds are weaker than covalent bonds by a long ways. So which structure is stabler, primary sequence or secondary? Well, of course, it's primary, right? What does that mean? That means if I take a protein and I break the hydrogen bonds in that protein, I can destroy its secondary structure. I won't destroy its primary structure, meaning it'll still exist as a polypeptide, but it will no longer have those same shapes that it had before. When I told you that shape was necessary for a function, structure was necessary for a function, if I destroy the shape, I destroy the function. The reason I cook my food is so I can destroy the proteins in the bacteria that would love to kill me, or at least eat on me. Okay? Heating destroys hydrogen bonds because it doesn't take much energy to destroy hydrogen bonds. That's how I boil water. I'm destroying hydrogen bonds. That's how I cook an egg. Okay? I'm doing something that we describe as denaturing that protein. And for most proteins, once I denature them, I can't put the pieces back. I can't put it back in that original structure. It won't go back. For most proteins. Not all, but for most proteins, that's true. So I kill organisms by cooking them. I kill organisms by washing my hands. Soap is a great way to disrupt structure of proteins. It actually does more of an effect on tertiary structure, as I will show you. But if I destroy the structure of proteins, I destroy the function of those proteins. Okay. So alpha helix, very important structure. As I said, alpha helix was discovered by Linus Pauling, for which he won the first of his Nobel Prizes. And it is an interesting structure. That's more of an attempt at a three-dimensional depiction, where we can see now those dotted lines showing some hydrogen bonds that are present. Okay? And you have to do some counting in there to figure out which ones, which amino acids and so forth, so don't sweat that too much. But the point is that interactions happen between amino acids that are close to each other. I like this one. This takes that alpha helix, and we look down the barrel of it instead of looking at the side of it. And the thing that jumps out at you if you look down the barrel of this guy is that the R groups are oriented where? Outwards. They're all pointed outwards from the helix, and duh, it sort of makes sense, right? Steric hindrance is, again, coming into the picture. Now, if we look at this, we say, well, these guys here are two. It's kind of hard to get the three-dimensional feel of this, but we can imagine that at least they're on the same side of that alpha helix. What if this guy's a big honking R group and this guy's a big honking R group? Do we suppose that this alpha helical structure would be stable? The answer is no, it would not. And so that tells us that some amino acids are really not going to be very compatible in the confines of an alpha helix. Some amino acids are not very compatible in the confines of an alpha helix because they've got R groups that are going to bump into each other. Okay. I did it again. Okay, and back. All right. Now, let's take a look at the Ramachandran plot. Now we can actually take real-world proteins for which we know the structure and say, what are the actual angles of those bonds? And when we do that, the theoretical structure told us there had to be something stable with these rotational angles. And when we look at the rotational angles that exist in actual alpha helices, The real world matches theory very well. It matches it beautifully. We see very rare structures up over here, okay, that are in a place that's really not very stable. That wasn't totally surprising, right? You're now left wondering, well, what's this big blob over here? And the answer is, it's the second major structure that we see in a polypeptide chain. Okay? It's known as a beta sheet. Okay? So first of all, here is where they occur. Beta strands actually occur in this region. And by the way, the difference between beta strands and beta sheet. Sheets are made up of strands. If you want to make a sheet, you have to weave strands of thread together, right? If you weave individual strands of beta strands together, you make a sheet-like structure. And that's why people sometimes confuse the two. The sheets are the individual pieces. If you arrange them in a certain order, you get the strands are the individual pieces. If you arrange them in a certain order, you get a sheet out of them. And I'll show you that in a second. Okay, so now, again, theory matched the reality, and that was pretty cool. And when we looked at the structure of beta strands, they turn out to be fairly simple. Now, that doesn't look too simple, but they're in the form of what we like to describe as a pleated sheet. That's where the sheet comes in again. Okay? If we think of a curtain and how a curtain is folded, we see, oh, God dang it. We see, in the case of the curtain, that it has a certain arrangement. It has a certain folding pattern that is very regular. And that's actually seen right here. Okay? Here is one beta strand on the top arranged with another beta strand on the bottom. And they're starting to form a sheet. If we had another one down here, we would start to see how this wall would happen of these molecules. What time is it? Okay, I'm going on a little bit. All right, so we start to see how that wall forms. More importantly, look at the orientation. This guy looks an awful lot like that first structure that I drew for you, which had what? It had up, down, up, down, up, down. A beta strand really only has two dimensions, up, down, up, down, up, down. It's different from a coil that has three dimensions. So in contrast to an alpha helix, a beta strand is largely a two-dimensional repeating structure. Now, don't worry about the arrows here. Okay? All it's showing you is it's going amino to carboxyl one way, and this one's going amino to carboxyl the other way, and that's not an important point. The more important point is, look how these strands are held together next to each other. Hydrogen bonds. There we are. The hydrogen bonds are holding together individual strands of the sheet. And they're oriented beautifully so as to, again, minimize the amount of steric hindrance. Do you suppose that if we have an R group that's right here, that's very large, it might cause a problem? If it's very across from one over here that's very large, the answer is yes, it could. All right? But one of the beautiful things, if you look at this, is the green guys, which are in fact the R groups, are oriented not in the middle between the strands, but in fact are perpendicular to it. Steric hindrance. Steric hindrance is orienting things so that the structure can be maximally stable. Okay, I've gone on a little bit longer than I wanted to, so let's take a break for a couple of minutes, and then we will dig into the next stuff.